shop owner has bought in the Santa or in any right bazaar.
Those type of plastics are known as thermosetting plastics. Comparison, there are 3 types.
Up, down, right, left.
I am not inferior to anyone.
We are Clara. We are top on the Everest. Congratulations.
I want to be a leader.
Hi Sweros, I am B.Srividya Swero studying 10th standard. I am from Dindi, Nalgonda district. In this competition, I have chosen subject physical science. Before I am going to start the session, I would like to wish all the teachers and my dear Sweros happy Teachers Day. Here, friends, I think already you are familiar with the words electricity and magnetism, right? Generally, we use these words in our day-to-day life. But up to 1820s, these two words electricity and magnetism are separated as physical phenomena. But the great scientist Oersted was established that there is a relation between the electricity and magnetism. Friends, is there any relationship between electricity and magnetism? Yes, definitely there is a relation between electricity and magnetism. And also friends, for example, if we take a coin, for a coin how there is a 2 sides, heads and tails, like that there is a vice versa. And here scientist Oersted was proved that electricity can produce a magnet. So by doing an experiment, he proved that every current carrying conductor acts as a magnet, and he proved that electricity can produce magnet. So in this there is a vice versa, that is today we are going to prove that a magnet can also produce electricity. Today in this session I will make you to understand that we can produce electricity by using the magnet on the topic electromagnetic induction. Friends, let us see what is the purpose to study electromagnetic induction and how does it helpful, whether it is really helpful to our day-to-day life or not. So, we should go ahead and study the concept of electromagnetic induction, and there are so many examples for this electromagnetic induction. Let me show the examples for electromagnetic induction, and the topics to be covered in this session are introduction, Faraday's magnetic flux, Faraday's experiment, Faraday's laws of induction, applications of electromagnetic induction. Friends, there are so many applications of electromagnetic induction, and also the most important advantage of using electromagnetic induction in our day-to-day life is there are so many applications. For example, let us see what are those examples. Here this is an induction cooker and a fast moving electric train, normally which we may not see in our India, but which we can see abroad. So we can call these trains are also as bullet trains. And here even one more surprising thing to know is even a wireless charging is coming into the picture. That means you can charge your mobile, maybe you are at somewhere. So this is a very interesting application of electromagnetic induction. And also friends, the great scientists like Michael Faraday have done several experiments to prove that a magnet can produce electricity and to make the use of electromagnetic induction in our day-to-day life. So before I am going to say about electromagnetic induction, I would like to say about magnetic flux. So why? Because magnetic flux is a kind of pre-represent of electromagnetic induction. So without having the clear idea of magnetic flux, it is very difficult to understand the phenomenon of electromagnetic induction. So friends, first let us know what is magnetic flux. Magnetic flux means nothing but here these are the lines, right. Here these lines are called as magnetic field lines, and in these magnetic field lines, here this is the area. So, here these magnetic field lines are perpendicular to area vector. So, when I talk about magnetic flux, I also talk about electric flux. Why? Because electric flux is also nothing but, electric flux means the number of electric lines or number of electrons which are passing through a particular area is said to be electric flux. So, again when I talk about magnetic flux, I would like to talk about orientation of area. Why? Because here let us friends once have a glance on this PPT. Here these are the magnetic field lines, right. So, the crossing of these lines varies with the orientation of area. So, that is why this orientation of area is treated as a vector quantity. So, here we can call this area as a area vector. So, here we have denoted this magnetic field lines with B and then this area vector as A. So, here this is the symbol of magnetic flux, that is nothing but phi. So, here phi is equal to the product of magnetic field and A. Magnetic field means B and A. So, here simply we can also say the magnetic flux as the product of average magnetic fields and area perpendicular times that it penetrates. So, friends, now we came to know what is magnetic flux. So, here let us prove this magnetic flux mathematically. Friends, once all of you look on this board, here let us prove the magnetic flux mathematically. So, here friends, we came to know that this is the phi. Phi is nothing but it is a magnetic flux. So, here phi is equal to B into A. Why I am writing it as B into A means magnetic flux. What is magnetic flux? Before we have discussed that magnetic flux is a product of magnetic field and area vector. So, here B is the magnetic field and A is the area vector. So, here phi is equal to B into A. So, here we can write it as phi is equal to BA cos theta. So, here let us consider one scenario to know to prove this magnetic flux mathematically. So, friends, let us see here. Here these are the magnetic field lines. So, in this magnetic field lines, this is the particular area through which the magnetic field lines are passing. So, here first of all we have to take one normal to this area vector. So, this is the area vector and here these are the magnetic field lines. So, here this is the normal. So, now this normal makes an angle with magnetic field. So, we should call it as theta. So, friends, do you know what is theta? Yes, theta means nothing but theta represents the angle between the magnetic field and the normal. So, here now theta what? Friends, can you say what is theta here? Yes, here it makes an angle 90 degrees. So, here theta is equal to 90 degrees. Let us substitute this value of theta in the equation given that phi is equal to BA cos theta. So, here phi is equal to BA cos, and what is the value of theta here? Yes, here the value of theta is 90. So, cos 90. And friends, in our mathematics generally we have studied in the chapter trigonometry, which is in mathematics, we have studied about sine values, cos values, tan values, right. So, friends, then what is the value of cos 90? Yes, here the value of cos 90 is 0. So, here phi is equal to BA cos 0. BA cos 0. So, friends, here the value of cos 90 is 0. So, here we can write it as phi is equal to BA into 0. So, here finally we can say that here phi is equal to 0. In this scenario, the magnetic flux is 0. And let us consider another scenario. Here this is another scenario. In this scenario, this is the area vector through which all these magnetic field lines are passing. So, here in this area vector, let us draw one normal. So, here it is a normal. So, normal makes an angle 0 degree, that is nothing but theta. So, here what is phi? What is magnetic flux? Magnetic flux means a product of magnetic field and area vector. Here these are the magnetic field lines and here it is the area vector. This is the area vector. So, here phi is equal to BA. So, here we can write it as BA cos theta. So, phi is equal to, what is the value of theta here? 0. Friends, now we came to know, in our class we came to know what are the value of cos and sin. So, here what is the value of cos 0? Yes, the value of cos 0 is 1. So, here phi is equal to maximum, that is here the magnetic flux is maximum in this second scenario. So, friends, now we have proved this magnetic flux mathematically. Now, let us see one more example for this magnetic flux on PPT. Friends, all of you see here, in this example here, this is the area vector. So, this is the area vector. So, in this area vector, these are the magnetic field lines which are passing through this area vector, and here we have drawn the normal. So, here this normal makes an angle with the magnetic field. Friends, here approximately the angle will be less than 90 degrees. Why? Because it is an acute angle, right? So, here the theta, there will be something value for this theta. So, we can write this magnetic flux as a product of this magnetic field lines and this area vector. So, here phi is equal to BA cos theta, product of magnetic field, area vector and angle. So, here here phi is equal to B perpendicular to A. Friends, this is one of the example for magnetic flux. Now, we came to know what is magnetic flux, and now we got a clear idea about magnetic flux. Friends, do you know why I told about magnetic flux before I am going to say about electromagnetic induction? Why? Because magnetic flux is a kind of pre-represent of electromagnetic induction. Without having the clear idea or without having the aware of the concept of magnetic flux, it is very difficult to understand the phenomenon of electromagnetic induction. Now, we are aware of the concept of electromagnetic induction. So, now let us enter into electromagnetic induction. Before I am going to say about electromagnetic induction, I would like to introduce one of the great scientists who is, can you say friends, who is he? Yes, once look at this PPT, here friends, who is he? Yes, he is Michael Faraday. Here this Michael Faraday was one of the great scientists who became the world most great scientist only due to little scientific education. And also friends, he is also called as father of electricity, and along with Michael Faraday, Joseph Henry is also performed several experiments to prove that a magnet can produce electricity, but the results which are given by the Michael Faraday was very accurate in the year of 1831. So, that is why he is treated as a father of electricity. And friends, here this one day while Michael Faraday was thinking, one question was raised in the mind of Michael Faraday. What that question is, can a magnet produce electricity? Yes, towards it Michael Faraday was performed several activities, several experiments to know that a magnet can produce electricity. So, he was performed one activity. Now let me show what that activity is. He has taken one electric bulb and then one bar magnet, and he has connected the two terminals of the electric bulb to the two ends of the bar magnet. So, after connecting these two terminals of electric bulb to the two ends of the bar magnet, he observed that here the bulb started glowing. That means Michael Faraday was observed that here the magnet is producing electricity. So, by doing this experiment, Michael Faraday was given a conclusion to us that a magnet can produce electricity. Okay friends, now let us do some experiments to prove that a magnet can produce electricity. Friends, before I am going to perform an activity, let me show what are the requirements for this experiment. So, here friends, do you know what is this? Friends, here this is a galvanometer, and here the requirements for this experiment is, this is a insulated copper coil. This is a insulated copper coil, and here this is a galvanometer. Friends, do you know what is galvanometer? Yes, galvanometer means nothing but galvanometer is used to measure the flowing of a current in a conductor. So, now friends, here it is the copper coil. here these are the copper coils which are surrounded, and these are the turns of a copper coil. So, now already in this experiment, first we have to take the copper coil and then we have to fix the two ends of the copper coil to the center 0 galvanometer. But already we have connected the two ends of the copper coil to the center 0 galvanometer. Okay friends, let me show one activity to know that a magnet can produce electricity. So friends, do you know what is this? Yes, here it is nothing but, friends, here it is a bar magnet. So for this bar magnet there are two poles, one is north pole and another one is south pole. Okay friends, while so now I am going to insert this south pole of the bar magnet inside the galvanometer. So here I am inserting the bar magnet inside the galvanometer. Friends, do you find what is happening here? See, again I am inserting the bar magnet inside the copper coil. Just observe the needle which is in the galvanometer. So now see, while I am inserting, what it happened? Yes, while I am inserting the bar magnet inside the coil, there is a deflection of a needle in the galvanometer. And also now again see, again I am inserting the bar magnet inside the galvanometer. So again there is a deflection in the galvanometer. That means here we can say that here the deflection indicates that current is inducing in the galvanometer. And now I kept the bar magnet stationary within the coil. Friends, see, now I place the bar magnet stationary within the coil. Is there any deflection in the galvanometer? Yes, there is no deflection. Why? Because before what I told, the deflection in the galvanometer indicates that there is a current induced in the coil, but now there is no deflection. That means simply we can say that there no current is induced. And also now and again I am just observe briefly. So here when I am removing the galvanometer, again there is a deflection towards right. Let us observe once again. Again I am inserted. So when I am inserted, there is what is the direction of the deflection here? Yes, here the direction of the deflection is towards left, and when I am removing, the direction is towards right. So friends, here we can say that the deflection in the galvanometer indicates that current is induced in this coil, and also the direction of the deflection indicates that the direction of the induced current. Now again this is the south pole, right? Now I inserted the south pole. So when I inserted the south pole, it showed direction towards left. That means the direction of induced current in this coil is towards left, and while I am removing, the direction is towards right. That means here the direction of induced current is towards right. And also friends, in this experiment we came to know that a magnet can produce electricity. Now I have performed this activity by inserting the south pole. Now let me change the pole of the bar magnet and let us observe whether it is similar or dissimilar when compared to the before experiment. So now this is the north pole. So now I am inserting the north pole of the bar magnet. See, once again I am inserting the north pole of the bar magnet. So when I am inserted the bar magnet, it showed deflection towards the direction right. So we can say that this experiment is quite opposite with before's experiment. So why? Because when I inserted the south pole, friends, in which direction the deflection is? Yes, when I inserted the south pole, the direction is towards left, but now it is quite opposite. That is, now the direction is towards right. And again I kept the bar magnet in the galvanometer within the coil stationary. That means I am not inserting, either I am not removing. So here the bar magnet is stationary within the coil. Friends, is there any deflection in the galvanometer? Yes, there is no deflection. Why? Because whenever the bar magnet is stationary within the coil, then no current is induced. So that is why the needle does not show any deflection if the magnet is stationary within the coil. So again before I am inserted the north pole and again remove the north pole from the bar magnet. See, while I am inserting, just observe the direction of the needle. While I am inserting, the direction towards right. The direction is towards right, and also while I am removing, the direction is towards left. So, here the direction of the deflection indicates in this galvanometer that this direction of the deflection indicates the direction of the insulator the direction of the induced current. For now, can you say in which direction the current is inducing? Yes. Now, I am inserting south pole. In which direction the current is induced? Here the current is induced towards left. So, here now we came to understand that a magnet can produce electricity, right. So, and also here now I have inserted only once and again I have pulled it out, right. So, let me do this experiment by moving the magnet in and out rapidly, and let us observe what is the deflection in the galvanometer. So, now this is the bar magnet, right. So, I am inserting the bar magnet, and inserting and pulling it out rapidly. So, while I am doing this, what is the deflection in the galvanometer? Yes, here the deflection is, while I am inserting the rapidly, the deflection is from center 0 galvanometer to right and center 0 galvanometer to left. So, here while I am inserting and removing, the deflection is showed from center 0 to right and center 0 to left. So, let me show this experiment on PPT. Friends, once now we have proved that electromagnetic induction, that means today we are discussing about electromagnetic induction. That means here electricity can produce a magnet can produce electricity. So, here as the name suggests, electromagnetic induction, we can say that we are going to learn something related to electricity, magnetism and induction. Okay friends, generally we have listened the terms electricity and magnetism in our daily life, but do you know what is induction? Yes, what is the term induction in your normal English? Yes, induction means nothing but to induce something or to produce something under the effect of electricity and magnetism. Now, we have induced the current in this, here in this experiment, in this galvanometer we have induced the current under the effect of magnetism. So, that is why we can call it as electromagnetic induction. So, basically we can also say electromagnetic induction as it produces electricity. Friends, once look at PPT, here it produces electricity due to magnetic fields. So, here before we have learnt about magnetic flux, right. So, while we learnt about magnetic flux, so here why the current is inducing means, here while I am inserting and removing means, here I am changing the magnetic flux. So, due to change in magnetic flux, the current is inducing. So, that is why here we can say that the current is inducing due to magnetic fields. And also let us here EMF is equal to delta phi by delta t. What is EMF? Yes, EMF means nothing but electromotive force. So, electromotive force is also said to be induced current. So, here EMF is equal to delta phi by delta t. So, before I am performing one activity, right. So, here this is the Faraday's experiment. This is a bar magnet, and in this bar magnet this is a north pole and here it is south pole, and this is a copper coil, and here this circle is can be indicated as galvanometer, and in this galvanometer this is the needle which shows us deflection. And also here the movement is, magnet is moving in. If we insert the magnet inside the coil or along the axis of the coil, it shows deflection towards right. Let us just observe the direction of the deflection. Here the deflection is towards right, and also here in this case, if the magnet is stationary, before we have also seen in the experiment, if I kept the magnet stationary within the coil, is there any deflection? Yes, there is no deflection. So, that is why here also here in this case the north pole of the bar magnet is stationary within the coil. So, that is why in this galvanometer there is no deflection. And also again here in this picture the magnet is pulled out, that means the north pole of the bar magnet is pulled out. So, here the deflection is showed towards in the direction of left. So here the direction indicates the direction of the induced current. So the deflection in the direction indicates the direction of the induced current, and also the deflection indicates that current is induced in the coil. And also friends, by doing all these experiments, Michael Faraday has given some of the observations to us. So let us see what are the observations. The magnitude of induced EMF is directly proportional to strength of magnet. Isn't it friend? Yes, here I have taken this. Here this is a bar magnet, right? So whenever before we are going to perform an experiment, if we take a if we take a magnet which is a full strength, so then automatically the current which is inducing within the coil increases. And also so here we can say that magnitude of induced EMF is directly proportional to strength of magnet, and the magnitude of induced EMF is also directly proportional to changing in magnetic flux. Friends, before you have observed that while I am before you are here we are saying that the magnitude of induced EMF, that means induced current is directly proportional to changing in magnetic flux, right. So while I am inserting and removing, what it is nothing but I am changing the magnetic flux. So due to this due to the changing in magnetic flux, here the current is inducing. So here we can say that the magnitude of induced EMF is directly proportional to changing in magnetic flux, and also the magnitude of induced EMF is directly proportional to number of turns of the coil. So friends, here it is a copper coil. In the galvanometer, here it is a copper coil. So if we increase the number of turns of a copper coil, then automatically the current which is inducing within the coil is also increases. So here by doing all these experiments, Michael Faraday is also told that magnitude of induced EMF is directly proportional to number of turns of a coil, and also magnitude of induced EMF is directly proportional to cross section area of a coil. That means, for example, here we are if we increase the cross section area, that means if this is a coil, right. So for this coil, if the radius increases, automatically the cross sectional area means nothing but the radius of the coil. So if the radius of the coil increases, automatically the induced current is also increases within the coil. So by doing all these experiments, Michael Faraday was told that the magnitude of induced EMF is directly proportional to strength of magnet, changing in magnet flux, number of turns of the coil, cross sectional area of the coil. And also friends, here now we came to know that a magnet can produce electricity. So right, and also now we have proved that a magnet can produce electricity by doing several experiments. And also here there is one condition for us to know the direction of a induced current. So friends, here let me show on the PowerPoint presentation. Here this is the Fleming's right hand rule. This Fleming's right hand rule will help us to know the direction of the induced current in the straight conductor. For example, here whenever we take the straight conductor, then we can easily know the direction of the induced current in the Fleming's right hand rule. So here this thumb finger is the motion of the conductor. This thumb finger indicates the motion of the conductor, and the forefinger indicates the direction for magnetic field, and here this is the middle finger. So this middle finger indicates the direction for induced current. So here if you have to know the Fleming's right hand rule, we have to stretch the thumb finger, forefinger and middle finger, but the angle between each finger should be 90 degrees. So if you see in this Fleming's right hand rule, here the angle should be, the angle from the thumb finger and the forefinger should be 90 degrees, and here exactly the angle is 90 degrees, and from forefinger and middle finger, here also the angle is 90 degrees. So in this case we can easily know the direction of the induced current of a straight conductor. And also friends, before I told that there are so many applications of electromagnetic induction. So generally in our daily life we use this electromagnetic induction in so many ways. So before we have seen the let us see in this galvanometer.